guys, so let's move on. Now, I want us to look at the following series, right? Look at this series, 1 over n, right? From what we have covered in other topics, we know that 1 over n can go to 1 and plus 1 plus 2 plus 1 plus 3, and the story goes on. Now, from what we have gathered in other tests previous to this chapter, we know that it always goes to 0, right? And in their case, it always converges. But this is not always the case. And through the integral test, we shall learn that this particular series can have certain conditionalities. So let us introduce the integral test, right? Now, the integral test is very particular, and it will help us in the P-series functions. What are P-series functions? P-series functions exist in this form, right? We shall have functions that look similar to these, and or even 1 over n to the power p. So that's why we call them the P-series. So let us move on to look at an example, right? Look at this example. Supposing we have a summation to infinity of 1n to the power p, right? With the integral test, we can sort it out like this. We can say that the limit as n as b we introduce tends to infinity of 0, right, to b, yes. Oh, let's change the limits to 1 because we wouldn't want to imagine a 0 here. Let's just change it to 1 here in this case, right? So let us assume that the limit as b tends towards infinity for b to 1, right, of 1 over x to the power p dx. I hope you realize how we have changed the x to the n just for the ease of working it out, right? So we have the limit as b tends to infinity, right, of, right, x to the power minus p plus 1 over minus p plus 1, right? If we remove out the constant here, we can bring it out here, 1 minus p, the limit as b tends towards infinity of x to the power minus p plus 1, right? Of course, if we try to put back the the limits in this case, we will know that we'll end up with something similar to the limit, right, as b tends to infinity of 1 over x to the power 1 minus p, right, moving o minus 0, because you know very well that this particular portion will also move towards 1 because x to the power, whatever it will be, right, in the end will always lead us back to, yes, okay, in the end we shall end up with this function. Let's cut the long story short. I'm sure you're very good at your algebra. And so when we end up with this function, this is the determinant function, because as we have realized before in the functions before here, the nth term test always pushed us to 0, but in this term we have in this particular function we have the option of choosing where we want things to move, right? Where do we want to move? And if, let's say, 1 over p is greater than 0, right? If 1 over p is greater than 0, that means p is less than 1, and that will tell us, because the region of, if 1 over p is greater than 0, then we are sure of one thing: a limit will exist, right? But if, let's say, p is equals to 1, we shall realize that we shall have 1 over 0, of course, which is not defined, right? We have to take that into consideration. But let's say p is less than 1, right? It shall be a bit very difficult to explain because of course, with p being less than 1, we shall have the interval moving, of course, towards I meant if p is greater than 1. If p is greater than 1, we shall have the interval moving towards negative infinity, which in actual sense is a divergence, right? It has no clear definition. So one thing we shall note, this p is the determinant for the integral test in the end, and it's very important for us to realize the integral test is only valid, right, for p less than 1, but not, right? But not for p equal to 1 or p greater than 1. I hope this will give us a better definition of the p-series test. Thank you very much.